Hi everybody, in this video we're going to talk about dynamic programming. We're going to look at two problems, the coin row problem and finding the max subarray within an array using Kadane's algorithm. So first, a definition of dynamic programming. So dynamic programming is a general algorithm design technique for solving problems with overlapping subproblems. The main idea of classical dynamic programming is, given a recurrence, solve for increasing inputs. So that just means if you have a problem that you can solve using a recursive algorithm, instead of using recursion, solve the problem using a table and solve moving forward. Okay, so we'll take a look at what that means. And then we're going to store all of our solutions to our subproblems in a table or an array or list. All right, so first let's look at the Fibonacci sequence. So if you remember the Fibonacci sequence, every number in this series is the sum of the previous two numbers. Okay. So this is a problem that you probably learned how to solve recursively, because you can see from the definition of the Fibonacci sequence on this slide, the first number in the Fibonacci sequence is 0, and then it's 1, and then every number from there on out is defined as f of n equals f of n minus 1 plus f of n minus 2. Okay, so that looks like a recursive solution. So here's your algorithm for the recursive solution. Like, this is your algorithm if you were going to write the code using recursion. So to find the nth number in the Fibonacci sequence, you would use this algorithm. F of n, then that would be your function. Then if n equals 0, you're going to return 0. If n equals 1, you're going to return 1. Otherwise, you're going to return f of n minus 1 plus f of n minus 2. Okay. So it turns out that looks like a simple algorithm. It turns out that, and you might recall this if you took analysis of algorithms, when you run this recursive algorithm, you're solving problems over and over again. So problems that you've already solved, you're resolving. Okay? And the runtime of this recursive algorithm is exponential. Okay, so it turns out we can use dynamic programming to solve this problem, and this dynamic programming algorithm runs in time O of n. Okay, so we're going to use it by solving for increasing inputs. That's what dynamic programming does. And we're going to store our results in an array or a list. So we're going to start with our base cases. So we know the first number in the Fibonacci sequence is 0, and the second number is 1. So we would initialize an array with the first value in the array is 0, and the next value is 1. So now we have the values that we need to start solving moving forward. So for each element in our array, we would solve for that value as f of I equals f of I minus 1 plus f of I minus 2. So we will have those values because we have our base cases stored in the first two values in the array, and then we can just solve moving forward. Okay, so let's take a look. Here's your algorithm. This is the actual code you would pretty much write. You would create an array. You would store 0 at f of 0 and 1 at f of 1, and then you would have a loop starting at index place 2. So for I equals 2 to n, you're just going to fill in your array f of I equals f of I minus 1 plus f of I minus 2. Okay, so the time efficiency for that algorithm is O of n, much faster than the recursive algorithm. And dynamic programming, you'll find that's the case, is that you can solve these problems much faster using dynamic programming as opposed to the recursive solution. Okay, so let's look at another problem, the coin row problem. So here is the definition of this problem. Okay, so there's a row of n coins whose values are some positive integers, okay, not necessarily distinct. The goal is to pick up the maximum amount of money subject to the constraint that no two adjacent coins can be picked up. Okay, so here's an example. So you have coins of denominations 5, 1, 2, 10, 6, and 2. So you want to pick up the maximum value that you can under the constraints that no two adjacent coins can be picked up. So forgetting about the dynamic programming solution, let's just look at what the solution is. So looking at those coins, if you solve this using a greedy method, you might pick up coin with the value 10 first. When you pick up that coin, you can't pick up 6, which is the next greatest value. Okay, so you pick up 10, you can't pick up 6. Okay, so what's the next one in line? The 5. So you can pick up the 5 because it's not adjacent to 10. So now you're at 15. So now what's the next coin with the greatest value you can pick up? So there's a 2 at the end of the array that's not adjacent to the 5 or the 10. So you can pick that one up. And your total value is 17. Okay, and it turns out that is your answer. So 17 is the max value here. So let's look at how we would get to that solution using dynamic programming. Okay, so if you look at this example, the top row here, we have the index place of the coins. The next row here is your row of coins. And then the next row is where we're going to store our solution. That's going to be our table where we store the solution. So the first thing you're going to do is you're going to fill in that solution array with your base cases. Okay. So if you have 0 coins, the max you can pick up is 0. So you can see that stored in the table there. If you have 1 coin, the max that you can store in your table is going to be that 1 coin, value 5. Okay, so let's look at the full solution here. So we have our base cases in the solution 0 and 5. Okay, so now we're going to start filling our table one by one moving forward. Okay, so our next coin has the value of 1. Okay, so at this spot in our solution array, we're going to ask ourselves, do we pick up that coin and then forget the previous coin? Or do we not pick up this coin and take the solution from the previous coin? Okay, so if we pick up that coin 1, we can no longer take 5. So 1 is not greater than 5, so we're not going to pick up 1. So our solution for coins 5 and 1 is 5. So let's move to our next coin 2. So again, we can pick up 2, and if we pick up 2, we can add it to coin 5, or we can just take coin 1. Okay, so let's take 2 and add it to coin 5. Okay, so now our total solution is 7. So we move on to our next coin, which is 10. So we can take that coin 10 and we can add it to our solution found at I minus 1, which is 5. Okay, so it would be 15. Or we take the solution found at I minus 1. Okay, so that would mean we wouldn't pick up the coin. But let's pick up the coin. So we move on to the next slot. So our coin is 6. So when we have coin 6, we can pick up coin 6 and add it to our solution at I minus 2, which would be 6 plus 7, which is 13. Or don't pick up coin 6 and take the solution at I minus 1. So let's take the solution at I minus 1 because that's greater than picking up coin 6. And then finally, our last coin 2. Do we pick up coin 2 and add it to our solution at I minus 2, which would give us 17? Or do we take the solution at I minus 1? Okay, so we're going to pick up coin 2, and then our solution is 17. Okay, and then here is your coin row algorithm. The time efficiency, again, we're just doing a linear scan through our coin array, and our time efficiency is O of n. Okay, so next is Kadane's algorithm. So here's the problem. So you're given an array of integers, which may include negative numbers. You need to find the contiguous subarray with the maximum sum. Okay, so here's our example. We have an array, several numbers, many of them are negative. So the maximum subarray sum is 6. Okay, and that is from the subarray 4, -1, 2, and 1. Okay, so let's look at how we can use dynamic programming to come up with that answer. Okay, so again, we're going to look at this table I have here. So we have our index place at the top. We have the value of the array, and then the next row would be an array storing our solution. So the first thing we want to do again is come up with our base case. So our base case is going to be the first element of our array, which is -2. So if we have an array of size 1, the maximum subarray is just going to be that value. Okay, so our first solution for an array of size 1 is going to be -2. So now we're going to solve moving forward. Okay, so now we're assuming that we have 2 elements in the array. So at each step in your solution array, you're going to ask yourself this question. You're going to say, what is greater, taking the value as it is, which would be 1, or adding that value to the previous solution? Okay, so adding 1 to the previous solution, which is -2, is -1, which is not greater than just taking the value by itself. Okay, so our solution here is 1. Okay, we're going to forget about the previous solution. Okay, so then we just continue to do the same thing. So our next value here is -3. So what's greater, -3 or -3 plus our previous solution? So we're going to take -2. It's -3 plus the previous solution. And then again, here at 4, what's greater, 4 or adding 4 to our previous solution? Okay, so that would be 2. So we're going to take 4. So you continue to do that. You fill up your solution array. And then your maximum subarray sum is going to be the max value found in this solution array, and that's 6. Okay, so here is your algorithm. The time complexity again is O of n. These slides are posted on kmalone.io, so you can look at this algorithm and the other algorithms found on that site. There's also some practice problems for you there. Okay, thanks. Good luck.